Astronomers have made an unexpected discovery using the James Webb Space Telescope. It spotted 6 massive galaxies that existed between 500 million and 700 million years after the Big Bang that created the universe.
The James Webb Space Telescope could be considered one of the most powerful scientific instruments of our era. It offers us the opportunity to observe the incredible evolution of galaxies spanning billions of years and uncover the mysteries of the vast and awe-inspiring universe. Recently, the telescope identified a structure that defies explanation. The telescope revealed the astonishing details that may have eluded the scientific community for years. Scientists find themselves perplexed, and some even assert that this discovery defies the laws of science and challenges established norms. What might this discovery entail? And how could it potentially reshape our understanding of the cosmos? Join us as we explore how the James Webb Telescope identified a structure that defies explanation and how it has shaken the very foundation of our understanding of the cosmos. Since the beginning of human civilization, people have been fascinated by the mysteries of the night sky. What exists beyond our planet? How did the universe originate? These questions have been a driving force behind our exploration of the expansive realms of space. In pursuit of these answers, we've developed exceptional tools that enable us to gaze into the cosmic depths. One of the most extraordinary inventions in this endeavor is the James Webb Space Telescope, named after the astronomer James E. Webb, a leader in NASA's early space program. This telescope transcends the ordinary. It functions as a time machine, allowing us to peer into the past and unravel the universe's secrets. In its mission to rewind time and study the genesis, characteristics, and development of galaxies while searching for exoplanets, the James Webb Space Telescope recently identified 6 previously unknown galaxies.
The James Webb Telescope has identified 6 galaxies that exist 500 million years after the Big Bang that are up to 10 times bigger than the Milky Way galaxy. That shouldn't happen. Something is wrong. We may have to revise our theory of the creation of the universe.
Scientists assert that these galaxies, due to their immense size, challenge our existing models of cosmology and physics. The intriguing question arises: how is this possible? And what defines these galaxies?
It's shocking because some of these galaxies were 13 billion light years away, and they had 100 billion solar mass of the stars. And so what that means is that we are viewing these galaxies very shortly after the Big Bang, only 600 million years after the Big Bang. I know it sounds like a lot, 600 million years, but our universe is 13.8 billion years old. So we're really looking at the infant universe when it was only 5% of its current age.
Before delving into the specifics of the James Webb Telescope's findings, it's crucial to highlight its groundbreaking attributes. As the largest and most powerful space telescope ever constructed, the James Webb Telescope marks a significant milestone in our quest to comprehend the cosmos. Its primary mirror, an enormous structure measuring 6.5 meters in diameter, consists of 18 hexagonal segments that unfold like an origami flower. This vast mirror, equivalent to the size of a tennis court, gathers more light than any other telescope, enhancing its ability to observe further and clearer than ever before. However, the mirror is not the sole feature distinguishing the James Webb Telescope. It also incorporates advanced infrared sensors, enabling it to peer back in time to the universe's earliest epochs. It captures light from the initial galaxies that emerged just 250 million years post-Big Bang. Traversing billions of years across the expanding universe, this light undergoes a wavelength shift from visible to infrared.
These are not baby galaxies at all. They're actually monstrous black holes. Black holes that formed after the instant of creation. That's baffling scientists because they don't fit in the normal sequence of the birth of a galaxy. So I personally think that we're actually looking at monster black holes where perhaps new laws of physics are emerging. And again, if you can figure all this out, there could be a Nobel Prize waiting for you.
The James Webb Telescope can discern this faint infrared light, unveiling ancient galaxies beyond the capabilities of any other telescope. The James Webb Space Telescope's mission is geared towards revolutionizing our comprehension of the universe. It aspires to unravel the mysteries surrounding the universe's formation, shedding light on the birth of stars and galaxies, the evolution of cosmic structures, and the potential existence of habitable exoplanets. By observing distant objects emitting light in the infrared spectrum, the telescope opens new perspectives into the cosmos, expanding the horizons of our cosmic knowledge. It also has the capability to permeate dust clouds, which obstruct visible light, uncovering concealed depths within the cosmos. The discovery of fresh galaxies carries immense importance in the field of cosmology. Each recently found galaxy signifies a fragment of the cosmic puzzle, offering clues regarding the composition and evolution of the universe. Through the examination of these remote galaxies, astronomers can acquire insights into the genesis of stars and planets, the dispersion of dark matter and dark energy, and overall configuration of the universe. The James Webb Space Telescope's proficiency in detecting faint distant galaxies has already resulted in groundbreaking revelations. In July 2022, the telescope captured images of galaxies that existed a mere 620 million years after the Big Bang, marking the farthest galaxies ever observed. These observations propel our comprehension of the early universe to unprecedented frontiers, exposing the initial galaxies that emerged from the primordial chaos. Presently, 6 new galaxies have been identified, distinguished by their unique characteristics unlike anything seen before. But what sets this telescope apart? The answer lies in its distinctive capacity to investigate infrared light, uncovering the concealed secrets of the universe. While the James Webb Space Telescope stands as the most substantial and potent space telescope ever constructed, it also represents a notable advancement over the Hubble Space Telescope, which has orbited Earth since 1990. The Hubble Space Telescope has transformed our comprehension of the universe by capturing striking visuals of galaxies, nebulae, stars, and planets. However, it has limitations, only perceiving a portion of the electromagnetic spectrum. In contrast, the James Webb Space Telescope can extend its vision beyond Hubble's visible light range, delving into the infrared emitted by the most ancient and distant cosmic entities. Differing significantly from the Hubble, the James Webb Space Telescope boasts a primary mirror with a 6.5-meter diameter, 3 times larger than the Hubble's. This size advantage enables the James Webb Space Telescope to gather 4 times more light, enhancing its ability to observe fainter and more distant celestial bodies. The James Webb Space Telescope's mirror segments are adjustable, allowing it to correct distortions or errors, ensuring superior image quality. Operated at -218 degrees Celsius, the James Webb Space Telescope is substantially colder than the Hubble's -123 degrees Celsius. This lower temperature elevates the efficiency of its infrared detectors, heightening sensitivity to faint infrared light. Additionally, the James Webb Space Telescope incorporates a sun shield, a 5-layer structure shielding it from the sun's heat and radiation. The sun shield maintains the telescope in darkness and coldness, establishing optimal conditions for infrared observations. The James Webb Space Telescope incorporates 4 scientific instruments, each tailored to explore distinct facets of the universe. These instruments comprise: the near-infrared camera is capable of observing the initial stars and galaxies along with the formation of new stars and planetary systems in the early universe. The near-infrared spectrometer is proficient in gauging the chemical composition, temperature, and motion of celestial bodies, as well as detecting water and organic molecules. The mid-infrared instrument is adept at examining specific entities such as dust clouds and stars in early formation, as well as the atmospheres of exoplanets. The fine guidance sensor, near-infrared imager, and slitless spectrograph are a combined set of tools for precise targeting and imaging in the near-infrared spectrum. This instrument also conducts searches for exoplanets by identifying their transits across host stars. A recent milestone for the James Webb Space Telescope was the identification of 6 previously unknown galaxies, constituting one of the telescope's most remarkable discoveries. The sheer size of these galaxies challenges our existing understanding of physics and cosmology, as they seemingly contradict the conventional notion that galaxies evolve gradually over time, from small to large. Scientists initially anticipated discovering only very small, young galaxies at this early stage of the universe's existence. The enigma lies in how these monsters manage to fast-track to maturity, a phenomenon that remains unknown, as explained by Ivo Labe, an astrophysicist at Swinburne University of Technology in Australia. These galaxies have reached such an advanced age that they originated when the universe was a mere 800 million years old, accounting for less than 6% of its current age. Remarkably, these galaxies shine so brightly that they outclass the entire Milky Way galaxy by a factor of 10. This implies the existence of an alternative mechanism for galaxy formation in the early universe, one that eludes our current comprehension. These entities stand as the ultimate cosmic mystery, and the James Webb Space Telescope remains the sole instrument capable of unraveling this puzzle. The inaugural galaxy identified, GNZ 11, stands out as exceptionally compact and dense. It holds the distinction of being the most distant galaxy ever observed, with its light having traveled over 13 billion years, arriving to Earth when the universe was a mere 330 million years old. What adds to the astonishment is that GNZ 11, despite its compact size comparable to our Milky Way galaxy, possesses a mass 89 times greater than that of the Milky Way. This poses a challenge to our understanding of how galaxies form, indicating that galaxies can attain colossal sizes in a remarkably brief period. The second galaxy, named GZ10, resides approximately 133 billion light-years away, displaying a brightness surpassing astronomers' expectations by almost 100 times, exceeding theoretical predictions. Astronomers now propose that GZ10 might harbor a population of stars undergoing rapid formation, emitting substantial light and heat. This potential scenario forces a reconsideration of our comprehension of star formation processes in the early universe, suggesting that stars could come into existence swiftly and efficiently during their initial phases. Moving on to the third galaxy, GNZ 9, located approximately 13 billion light-years from Earth, it mirrors previously discovered galaxies by featuring abundant heavy elements like oxygen, carbon, and nitrogen. These elements, crucial for life as we understand it, were generated in the cores of massive stars that exploded as supernovae, enriching the surrounding interstellar medium. The presence of heavy elements in GNZ 9 indicates that star formation and supernovae events were already underway in the early universe, marking a significant progression toward the potential emergence of life. It also suggests that, even at this early age, the universe exhibited chemical diversity and complexity. The fourth galaxy, identified as GNZ 8, is situated in close proximity to the preceding one and features a disk with a notably intricate structure, challenging established models of galaxy formation. Conventional wisdom suggests that gravitational interactions within galaxies give rise to disks, but the early universe's turbulence seemed incompatible with such disk development. The existence of GNZ 8 raises the possibility that disk formation might have taken place earlier than previously assumed, potentially reshaping our comprehension of galaxy evolution. Furthermore, it illustrates that galaxies could possess well-defined shapes and structures even in the disorderly conditions of the early universe. Moving on to the fifth galaxy, GNZ 7 stands out for its exceptional richness in dust, a pivotal component for the formation of planets. Dust particles serve as the fundamental building blocks for rocky planets, and their presence in the galaxy suggests that the formation of planetary systems might have commenced in the early universe. This discovery is noteworthy, suggesting that the prerequisites for planet formation are already established in certain galaxies, paving the way for the potential discovery of ancient planets and, perhaps, indicators of life. Finally, the sixth and last galaxy, GNZ 6, diverges significantly from the others, displaying a surprising redshift, a metric indicating how much the object's light is stretched due to the expansion of the universe. The redshift of this galaxy is slightly lower than anticipated for its distance, suggesting a potential location in a universe region with a somewhat slower expansion rate. This discovery poses a puzzle, hinting at the possibility of non-uniform expansion in the universe and variations in expansion rates across different regions. Such findings could deeply impact our comprehension of the universe's nature and origin. The question then arises, what do these galaxy discoveries signify for our universe? One of the most significant implications is the suggestion that galaxies might have formed much earlier than previously assumed. While not the oldest galaxies observed by the James Webb Space Telescope, launched in December 2021, 4 galaxies were previously identified dating back to around 350 million years after the Big Bang, albeit smaller in size. In contrast, the newly discovered galaxies contain much more mass and are comparable to the Milky Way, exhibiting features challenging our current understanding of galaxy formation and evolution. The identification of galaxies existing over 350 million years after the Big Bang challenges the prevailing notion that galaxy formation commenced around 500 million years after the Big Bang. This perspective is rooted in the idea of a dark period, known as the Dark Ages, following the emission of cosmic microwave background radiation. During this time frame, the cosmos was filled with neutral hydrogen gas, absorbing light emitted by the initial stars and galaxies. Only after the recognition of this gas by radiation from the first stars and galaxies did the universe regain transparency, allowing the observation of light from the early galaxies. However, the emergence of new galaxies implies that the Dark Ages might not have been as dim as previously thought, suggesting the universe could have undergone extensive star formation much earlier than anticipated, remarked Dr. Emma Chapman, an astrophysicist at the University of Nottingham. Additionally, the identification of galaxies boasting remarkably high stellar masses, like GNZ 11, hints that star formation in the early universe might have occurred at a much swifter pace than previously assumed. These colossal galaxies came into existence within a few hundred million years after the Big Bang, indicating an exceptionally efficient star formation process during the early universe. This challenges the traditional belief that early universe star formation was gradual, constrained by gas availability and cooling mechanisms. It also prompts questions about how these galaxies achieved significant growth in such a brief period, and the influencing factors behind their rapid development. Thirdly, the observation of galaxies exhibiting remarkably structured disks, like GNZ 8, poses a challenge to the current models of galaxy formation. While disks are believed to emerge from gravitational interactions within galaxies, the tumultuous conditions of the early universe seemed inhospitable for their formation. GNZ 8's existence implies that disk formation might have taken place earlier than previously assumed, potentially reshaping our comprehension of galaxy evolution. This discovery also underscores that galaxies can possess a well-defined shape and structure even amid the chaotic environment of the early universe. Furthermore, the detection of heavy elements, like the case of GNZ 9, within galaxies suggests that supernova explosions from massive stars responsible for producing these elements occurred earlier than initially thought. These crucial elements, fundamental for life as we know it, originated in the cores of massive stars that concluded their existence as supernovae, enriching the surrounding interstellar medium. The presence of heavy elements in these galaxies implies that the chemical progression of the universe might have advanced more swiftly than previously perceived, potentially influencing the formation of planets and the potential for early life. It also hints at the universe's chemical diversity and complexity. Lastly, the identification of these early galaxies implies a potential necessity for revisions to prevailing cosmological methods. These models must now accommodate the earlier emergences of galaxies, the escalated rates of star formation, and the existence of heavy elements in the early universe. Scientists must elucidate the origin and characteristics of dark matter and dark energy, entities believed to govern the universe, yet shrouded in mystery. However, some scientists caution against hastily revising cosmology. They highlight the Standard Model's remarkable success in explaining various cosmic phenomena, including cosmic microwave background radiation, the universe's large-scale structure, and its accelerating expansion. Certain researchers propose that the observed objects might be concealed in supermassive black holes. They suggest that the perceived starlight in the images could be gas and dust drawn in by these black holes' gravity. Emma Curtis Lake, an astronomer at the University of Hertfordshire, underscores the limited understanding of the formation and growth of black holes in early times. He asserts that this doesn't conflict with cosmology, but rather introduces new physics for comprehending their formation and growth, leveraging previously unavailable data. To validate their discoveries, researchers could capture a spectrum image of the identified objects, providing insights into their age. Galaxies from the early universe appear highly redshifted to us, indicating the stretching of light during its journey to Earth. A higher redshift value corresponds to greater stretching, revealing a more distant and aged galaxy. Through spectroscopy, scientists can ascertain whether the proposed galaxies, labeled as high redshift candidates, genuinely reflect their apparent age or if they are merely intrinsically reddened galaxies from a more recent era, according to Ethan Siegel, a theoretical physicist. This verification process becomes instrumental in confirming or refuting the hypothesis that these galaxies represent universe breakers, challenging our existing cosmological models. While Joel Leah, an astronomer and astrophysicist at Penn State, acknowledges the need for additional observations to validate the findings. He emphasizes in the statement, "Regardless, the quantity of mass we discovered indicates that the known mass in the stars during this era of our universe is up to 100 times greater than previously estimated. Even if we have the sample, this still signifies a remarkable change. This revelation suggests that the early universe exhibited much greater activity and dynamism than previously envisioned. Star formation appears to have been considerably more efficient and rapid than assumed. This raises intriguing questions about how these massive galaxies shaped the universe's evolution and the impacts they exerted on the surrounding matter and energy. The pivotal role played by the James Webb Space Telescope in these revelations is anticipated to be expanded upon by future space missions. The Vera C. Rubin Observatory, slated to commence operations in 2024, aims to conduct a comprehensive survey of the sky, enabling astronomers to identify and examine an extensive array of galaxies, including those at considerable distances, similar to the recently discovered ones. By delving into the formation and evolution of galaxies, we can glean insights into the characteristics of dark matter and dark energy, the chemical development of the universe, and the potential for extraterrestrial life. Achieving this necessitates future cosmological investigations that strive to integrate these diverse realms, contributing to the formation of a comprehensive understanding of the universe from its earliest stages to its current state. Such an undertaking will demand collaboration among astronomers, physicists, and other scientists, fostering a deeper understanding of the vastness and intricacy of the cosmos. With ongoing and forthcoming discoveries, scientists and astronomers may find themselves revisiting fundamental concepts and reconsidering widely accepted theories about the universe and its workings. The field of science buzzed with excitement and curiosity as the James Webb Space Telescope's detection of 6 unprecedented galaxies continued to perplex astronomers and researchers. In response, a team of daring scientists embarked on a mission to unravel the mystery of the cosmic lattice. Focused on GNZ 11, the most remote galaxy ever observed, astronomers employed the James Webb Telescope's advanced instruments for spectroscopy. This method aimed to ascertain the galaxy's true age and origins, settling long-standing debates within the scientific community. The results were truly remarkable. GNZ 11's spectrum validated its ancient existence, aligning with its distant position in the early universe. It wasn't an illusion or a misidentified, intrinsically reddened galaxy. It stood as a genuine relic from a bygone cosmic era. This revelation underscored the necessity for a fundamental shift in cosmological understanding. Yet, there was more to unveil. As scientists meticulously scrutinized the data, an unexpected pattern surfaced, one that challenged their preconceptions. The galaxies, GNZ included, were not haphazardly scattered in space. Instead, they formed an interconnected network of filaments resembling a cosmic lattice. This cosmic framework differed from anything previously observed. Its existence challenged the conventional understanding of the universe's large-scale structure, where galaxies were expected to be distributed more randomly. The presence of this ordered, interconnected structure hinted at a cosmic organization that defied current comprehension. As astronomers grappled with this newfound cosmic mystery, they found themselves compelled to pose profound questions about the nature of the universe. Did this lattice reveal hidden cosmic forces, or the influence of dark matter? Could it provide insight into the elusive dark energy responsible for the universe's accelerating expansion? In the quest to unravel the secrets of this cosmic lattice, scientists embarked on an ambitious endeavor to map its extent. Their goal was to identify more galaxies connected by these filaments, determining whether this phenomenon was unique to the initial sextet, or a pervasive cosmic architecture. As data continued to flow in, the cosmic lattice unfolded as more than an isolated phenomenon. It emerged as a fundamental feature of the early universe, intricately connecting galaxies across vast cosmic distances. This revelation posed even deeper questions about the underlying structure and evolution of the universe. A captivating hypothesis surfaced, suggesting that the cosmic lattice might be a vestige of the primordial cosmic web, the foundational structure upon which galaxies took shape. This notion implied that these filaments played a crucial role in guiding the growth of galaxies and shaping the cosmic terrain. This concept opened up new avenues of exploration as astronomers delved into understanding the physics behind these enduring filaments, stretching over billions of years. Yet, amidst these revelations, we are left pondering, what other surprises wait us as we continue our exploration of the unknown galaxies? As scientists delve deeper into the cosmic, astronomers now grapple with unraveling the mysteries held within this intricate structure, pondering the implications for our comprehension of the universe's past, present, and the enigmatic future that lies beyond the edge of known galaxies. Thanks for watching this episode of Space Wind. If you enjoyed the content, give it a thumbs up and stay tuned for more videos.